All right. It's been a minute since I've used Microsoft Teams to record lecture videos like this, so we'll see how this first one goes. Anyways, we're going to start talking about charges and conductors and insulators. Basically, what are charges? How are they formed? What counts as a charge? And then what can you put them on, a conductor and an insulator, right? So, some of the topics that we'll be covering include just definition of charge, uh, where those charges come from. So atoms, electricity, electrons, protons, going all the way down to like polarization and charging by induction. So the modern names for two types of charge are, and then you've probably heard of them, are positive charge and negative charge. All right. Now, actually, Benjamin Franklin, this guy, actually established this convention. So he basically come up with the whole idea of positive and negative based on the fact that if you take a glass rod, like the one down here in this GIF, hopefully the GIF is playing for you. If you take it like a glass rod and you rub it with silk, okay, he decided, well, that was a positive charge. Okay, that's fine. You can make up that definition. Now, he also said with the glass rod and the silk, anything that attracts it is going to be negatively charged because opposites attract, right? So this was the whole definition. So a plastic rod rubbed with wool, okay, would be negative. So these two rods would attract each other. Now, this is purely by convention. You'll notice that we have four different materials here. We have a glass rod versus a plastic rod. We also have silk versus wool. Okay, so clearly it depends on the material what becomes positive and what becomes negative. So I'm going to leave a note. Depends on the material. Right? Um, it actually wasn't until many years later that electrons and protons were discovered. Okay, I'm sure you all have heard of these, but the whole idea here is that electrons were found to be attracted to that whole charged glass rod idea. So electrons were attracted to the charged glass rod. Um, Protons were actually repelled. Okay. So this tells us, and you can sit there and think about it, or just follow along in the text. It sort of explains this as well. So by convention, okay, that's important. By convention essentially just means this is the way we defined it. You have to deal with it. So by convention, by that original definition, this means that electrons have negative charge, protons have positive charge. Okay? So electrons are negative, protons are positive. Now, it's important to note that this could be oppositely defined. Okay, that's the whole thing of like by convention. That's all that means is this is just how we set it up, so we're running with it. Um, Actually, in hindsight, and if any of y'all decide to like go into a um, electrical engineering program after this, if you want to transfer to like NC State or Charlotte to do electrical engineering, you'll find that it would have been so much better if Franklin would have made the opposite choice. If he would have said electrons are actually positive, that would have made things in the math work out so much better in more advanced electronics. So when you're thinking about how uh, current flows through a circuit later on in this course, or later on if you want to be an electrical engineering major, um, and things are starting to get weird in the math, you can thank Ben Franklin. Okay, now let's talk about exactly where these electrons and protons live. So an atom consists of a very small, dense nucleus. Okay, it's surrounded by much less massive. It's surrounded by much less massive orbiting electrons. Okay, so we have this nucleus here, and then you can see we have, it looks like one, two, three, four, five orbiting electrons. Now, the thing with these electrons, the orbital frequencies, so how fast they're zooming around the nucleus, their frequencies are so large that the electrons sort of form a cloud around the nucleus. And if you ever take quantum mechanics in the future, you'll learn that you can't think of the best way to think about electrons is sort of like a distribution, they're smeared around the nucleus of an atom. So this is sort of like a cloud. I apologize for coughing, but I do have a nasty cold. I don't think I could get through a video right now without coughing. So again, I do apologize. Um, so the nucleus, since we have this cloud of electrons, the nucleus itself um, is actually a structure consisting of both protons. Okay, so we have our negative outside, we have our protons inside. Um, we also in the nucleus, in addition to the protons, we actually have neutrons, and neutrons they don't have a charge. They have mass. There's a thing. It's a thing that has mass and it exists, but they have no charge. Um, so the atom is actually held together by the attractive electric force between the positive nucleus and the negative electrons. Remember the two rods charged two different ways will actually attract each other. So this is the same idea. So we have the positive nucleus, negative electrons, and those actually attract each other. So that's how the atom is held together, more or less. Um, so if you're interested, we have the mass of the electron and protons here. You'll notice that the proton is actually much heavier. Uh, they're supposed to say heavier. So the proton's actually much heavier, but they have the same charge. We represent the value of the charge as just E positive. Well, I do. The textbook just uses the letter E, which is also Euler's number, and that really gets on my nerves. But I prefer to do E positive for a proton and E negative for an electron. We'll talk about what that specific number is shortly. One of the most important discoveries is that charge is kind of like mass in that it's an inherent property, it's an intrinsic property of electrons and protons. It's just something they have. So electrons and protons do have equal magnitude, but opposite sign charge. So we can write that mathematically. We can say that the magnitude of an electron, or the value of E, is equal to the value of the electron. The E values are the same. It's just one of them's positive and one of them's negative. So without the absolute value signs, the proton is a positive number, the electron's a negative number. Now we have this atomic level unit of charge, okay? E. This is one of the very few things I don't like about the textbook. I hate that it uses E because that could also be read as Euler's number. Um, but nonetheless, uh, this charge is the basic charge of ordinary matter, okay? And those electrons and protons are what make up those basic charges of ordinary matter. Normally, we represent charge by the symbol Q, lowercase q for charge. Um, we can actually calculate or at least describe um, a everyday object, a macroscopic object, as having a charge given by this equation here. So if we want to know its charge, we can say, well, we could take the number of protons, okay, this n sub p, and multiply by the charge they have. They all have the same charge. So we can multiply by that number. Then we could subtract off, essentially take the difference, take away the negative amount that's sort of canceling out the protons. So we can count up the negative electrons and then multiply by their magnitude, which is just the negative fundamental charge value, e to the negative. And then essentially all we get is we just get the difference in electrons and protons, and then that's just multiplied by uh, that fundamental charge constant. Um, so for most macroscopic objects, usually they're neutral. They have an equal number of protons and electrons. So if that's the case, you'll notice from the equation, if NP and NE are the same, well then Q equals 0, and that's no charge. We can also talk about ions. Um, so this is essentially, an ion is essentially just a charged atom or molecule. Notice I said on the last slide, everyday objects usually have an equal number. So an ion is a case where that is the numbers are actually different. So an ion is essentially a case where these numbers are actually not equal. So if an object has more protons than electrons, then it's positively charged. In the other case, if it has more electrons than protons, then it's negatively charged. So whichever one dominates is the type of ion you're going with. You'll notice that an object's charge will always be an integer multiple of E. And that makes sense because we defined it that way. Remember, we said that the charge, no matter what, is this, these are all integers. So we have the difference in these two, whoops. So we have the difference in these two values multiplied by E. Now we know that in P and in E are integers, right? That's going to be our natural numbers here for the math folks. If these are integers, that means Q is always going to be a multiple of E, because in the parentheses here, this can only be a whole number. All right. So the fact that it's always going to be like 1E, 2E, 3E, a million E, um, or maybe even like negative 1,000 E, the fact that it's always a multiple of E is called charge quantization. We have quantized those steps. It can't be anything in between. It's always going to be a multiple of something. Um, so when this happens, um, uh, usually objects acquire a positive charge not by gaining protons, but by losing electrons. Turns out it's really hard to lose protons. So generally, um, uh, this number here does not change. NP does not change. Generally, if you're going to lose electrons or gain or if you're going to become positive, it's because you're losing electrons. And of course, the process of stripping away those electrons is actually called ionization. So if we look at these images over here, we do have a positive ion. So that means we have a net positive charge. You can count 5 protons in here, and then one, two, three, four electrons. So in this case, we see that there's more protons than electrons. So we have a case where NP is greater than NE, which means we have a positive ion. Similarly down here, we have what looks like to be five protons and one, two, three, four, five, six electrons. So the number of electrons is actually greater than the protons. And in this case, we know that it's going to be a negative ion since the electrons are dominating. This is more of a chemistry thing, but an atom that is missing an electron is called a positive ion or a cation, and its net charge is plus E. This is just missing one, right? Because if it were missing two or three or four electrons, then we'd have a number out here in front, an integer. But if it's just missing one, then its charge is plus E. An atom that has an extra electron is called a negative. Wait, yes, an atom that has an extra is called a negative ion or an anion. And its charge, of course, since that one electron is going to prevail, is going to have a charge of E negative. Generally, molecules are electrically neutral, but you can create molecular ions if you break bonds in a very specific way. So if you imagine some sort of molecule here, essentially what can happen is you've got several bonds in here, and then by friction, if you break this molecule up, what could happen is the distribution of electrons throughout essentially could, as you slice this thing in half, you could isolate some of the atoms on one side, and you'll notice that there's a positive here. Basically just means there's one less electron on the left. Then we also have a negative here. Basically one more electron on the right. And you've created two ionized um, molecules, so molecular ions, just because as this is split up, an electron needs to decide which side it's going to. And that's going to cause one side to have one less and one side to have one more. Okay. Um, so we've been talking about charges and where they come from, the electrons and protons. Something to think about. One of the most important discoveries here is that, and you've sort of hopefully have figured this out so far, um, as electrons move around, just like in that ion that we sort of split and we had an electron decide which side it wanted to go to, um, it turns out that charge is conserved, just like energy, just like momentum from physics 1. Uh, this is the law of conservation of charge. So it turns out charge is neither created nor destroyed. It can only be transferred to one object from another as electrons and ions move about. So the number of electrons and the number of protons and everything, that stays the same. What happens is the total number in a system doesn't change, just they move around. Their movement is what causes these effects that we see in the natural world from generating a charge or a discharge or something like that. So the total amount of charge remains constant. Okay, so this will be important later, just remembering that the number of electrons you start with should be the number of electrons you end with. Right. So we've talked about these charges, where they come from. Now let's talk about where we can put them. So we have conductors and insulators. Okay. Um, Conductors are called conductors because they're really good at moving electrons around. Insulators are called insulators because they're really bad at moving electrons around. Okay, so conductors are good at this, insulators are bad at this. Um, Both of them, though, can be charged by friction, just like those rods in that GIF where someone had the rod and they were charging it with a cloth, like wool cloth. Um, You can do that to both conductors and insulators. So if you rub a glass, okay, this sentence is interesting, so let's sort of break it down here. I've got two sentences in one. So we have, if you rub a glass rod with silk, you transfer electrons from the rod. However, so we're taking from the rod using silk, and it's a glass rod. But if you rub a plastic rod with wool, you'll transfer electrons to the rod. So this is actually called the triboelectric effect. And this is where electrons go depending on the materials that are being rubbed together. Okay, so let's see. I need to describe this. So we'll say the triboelectric effect is where electrons go depending on the material. So, I mean, this sentence here basically shows that in some situations you can have electrons go to the rod. In other situations, you can actually take them away. So the lab that you'll be doing this week actually has some components dealing with the triboelectric effect. So when we do this, when we charge an insulator by friction, essentially what happens is we leave patches of molecular ions on the surface, but these patches are immobile. So the important thing here is patches, because it's sort of blotchy charge, and then the ions on the surface are immobile. They don't move around. So you can see here in our insulator, we have all these atoms. They have a nucleus, they have core electrons, they have valence electrons. These valence are essentially outer electrons. They're tightly bound to the nucleus. So you may have uh, excess of electrons around these nuclei, but they're not going anywhere. They make up a net negative charge here, but they're not flowing through the material. It's just sort of localized negative charge. But in a metal, the outer electrons are only weakly bound. Okay, so this is like a conductor. Since they're weakly bound, they are very mobile in a conductor, like a metal. And therefore, these electrons are actually charge carriers. So here, let me see if I can zoom out more. Yep. So here, what you see is a whole sea of electrons, the way the book describes it, and a lot of physicists will call it a sea of electrons. Basically, all those outer electrons are free to move about the whole material. So you get um, lots of electron motion in a conductor, not so much in an insulator. That's why conductors or wires are made out of metal because metal is really good at moving electrons around. All right, let's discuss charging. How do we actually get these electrons on here? Um, so obviously we can take like plastic and wool, rub it like here in this picture. You can see that electrons are going to move from the wool to the plastic because the wool winds up being positively charged and the rod winds up being negatively charged. Since the protons don't really move, that means electrons jumped over to the plastic rod. Um, that's the case for an insulator, an insulating rod. It's still sort of localized, but if we think about doing the same thing with this plastic rod, and then we move it over to a conductor. Remember, this is an insulating rod, so let's take this rod, move it over to a conductor. So it turns out what's going to happen is you touch the plastic rod to the metal, and you'll notice that the electrons, they start moving down into the conductor because there's an excess buildup of electrons on the plastic. We touch a conductor like this metal. At first, they are isolated just up in the corner, but very quickly, because they're the same charge, so they're going to repel each other. So that's what's said here. Just like positives and negatives attract, like charges are going to separate. Like charges. So even though they're all in a clump, they hate being around each other, so they spread out. So it turns out that once this happens, once they are situated on a conductor, they move in such a way so there's no net force on any charge, right? Because they have all the repulsive force at the beginning. They hate that, so they're going to move out in such a way that there's no net force trying to move them anymore. There's still forces acting on them, but they're all balanced out. So you can think about it sort of like Newton's first law, F equals, or the sum of the forces equals zero. That's what these electrons are after. They want to situate themselves so all these forces, when you add them up, actually cancel each other out. So in an isolated conductor, that means all the excess charge is actually going to be located on the surface of the conductor. And that makes sense if you think about it. If you have some sort of metal block here and you put a bunch of electrons on it, electrons hate being around each other, so they're going to push out as far as they can to get away, which means on a conductor, your excess charge is always going to be on the surface. Okay, we talked about charging. How could we can move charges onto an object? Let's talk about discharging. So anytime you have two conductors in contact, they're going to share the charge that was originally just on one of them. Okay, if we have two conductors here, let's do this. Two conductors here, one's charged, one's not. As soon as you touch these two conductors together, they become one object. And electrons hate being around each other, so they're like, ooh, look, more space. So then they can spread out even more. So that's why when two conductors touch, you get this shift in electrons. Okay, so it turns out that moist air is a poor conductor, but it's conductive enough to where a charged object will actually slowly lose their charge just because they're in contact with the air over time. Another way to discharge is actually through grounding. So an object that is connected to the earth by a conductor, so essentially a wire, any object that's connected by a wire to the earth, um, or any conductor, basically anytime charge builds up on it, electrons hate being around each other, so they have this escape to the earth, and then they have the whole planet to distribute themselves over. They want to go to that space. So if you have, like a lightning rod here in the picture, that excess charge that gets built up on the lightning rod or in the clouds, uh, if you give it a path to like distribute on the whole Earth, it's going to take it. Um, this is why if you have like your computer, it's essentially grounded to the battery. So if you ever get like a shock from your computer, all that excess charge on you is basically just going into the computer and then going to the negative terminal in the battery. So the whole point of like being grounded is to remove any charge that you don't want on an object. So building up a big excess charge we know can be unsafe, so grounding it will keep that from happening. That's the whole point, and it's more or less a safety thing. It just is a way to keep things neutral. And you can see here, in the case where we have a lightning storm, we have excess charges. They want to move somewhere else, so they'll go through the lightning rod. We don't want excess charge on our building, so the lightning rod is there to make sure that those excess charges actually get put into the ground and not on the building. Because if your building is highly charged, as soon as somebody tries to open the front door of your building, well, they're going to touch this highly charged big structure and probably die. All right. Now we've talked about charging, discharging. Uh, let's talk about a weird phenomenon where we can actually take a neutral object and give it the appearance that it's kind of charged. Okay. And this is called charge polarization. Basically, a charge polarization is just a slight separation of positive and negative charges in a neutral object. So the point here is it is neutral. It's got the same number of charges, positive and negative, but we're going to redistribute them, hence the slight separation. We want to redistribute them so we can sort of get some charge type effects, but the overall object is still neutral. So you can think about it in terms of like taking a charged rod. Okay, this here, let's see if I can, let me read the bullet point, then I'll zoom in. So we're going to take a charged rod, we're going to move it near a metal object. Okay, and that charged rod is going to affect the sea of electrons, so all those free flowing electrons. Basically, what's going to happen is we're going to move the sea of electrons, and anywhere it moves from, you're just left with those protons in the nuclei. So you can see here, what we're doing is we are taking a positive rod and moving it beside this conductor, okay? So all the electrons, they're oppositely charged, so they're attracted to the positively charged rod. The electrons want to be on it. Okay, notice there's no touching, right? This isn't a charging by a conduction or anything. There's no touching, but the electrons are attracted. At the same time, as that happens, all the electrons are moved away, leaving just these positively charged protons in the nuclei over here, right? Because in a neutral object, the electrons will be everywhere, but they get pushed, since they get moved over to one side, you sort of leave a deficit on the right-hand side, the deficit of electrons, if you will. Um, Same thing with like this electroscope. We can put a positively charged rod above it. Ooh, that's supposed to be a plus sign. Wow. Let me try that again. There we go. So we can put a positively charged rod above it. All those electrons are going to want to go toward the rod, which means we're going to have a deficit of electrons down here. And when that's the case, it turns out that both of these little leaves on the electroscope, they're going to have a net positive charge since all the electrons left. So they're actually going to sort of move apart because these leaves are on like hinges. So when you do this with an electroscope, and you can look it up online if you'd like, anytime you start moving charges around, if you can get a same charge on each leaf, you'll see them separate and they'll spread out. So the net force toward the charged rod, because we have charges, we know that they're attractive or repulsive, so we know we have some sort of net force. we have attraction and repulsion going on at the same time, but one of those is going to win out. So that's the polarization force that we're talking about here. And this polarization force arises because the charges in the metal are separated, okay? Not because the rod and metal are oppositely charged. Now, that's what I meant earlier when I said we have a neutral object, but we're moving charges around to sort of make them act like they're charged. Okay, so they're not the two objects, rod and metal, are not oppositely charged. We're just making the metal sort of act like it. And that's due to charge separation. Okay, so looking at this again, you know that we're going to have, in this situation where we have the rod and the metal, well, this is an attractive force because they're opposite charges. Notice how this vector is much larger than the others. Okay, so this is the vector from the force vector from our electrons. Now, other charges, such as these protons down here, they're the same as the rod. Okay, so they want to get away. So these are the same as the rod. These are opposite. So you have this force vector from the proton electrons trying to bring them together. You also have a force vector from the protons trying to push them away. Now you remember a net force is if we just sum up all of the forces. And it turns out, if we do that, we have a big up force and then a not so big down force. Our net force, it shows us that the upward force is going to win out at the end of the day, uh, just because that repulsive force is just not as strong because they're further away. So the positive interaction, these protons are actually further away, so they're weaker. Further away. So you can see the distance does matter. So from here to here makes this interaction stronger than these positive ones down here. I've got that noted here. Since the electrons are closer, they're going to win out. That force is going to be stronger than the positive repulsive force. So, whoops, let's change my slide. Two opposite charges with a slight separation between them, like we've been talking about. This actually forms a dipole. Let me switch back to red. Okay. And di meaning two, pole just being like a point, more or less. Um, you can create this polarization effect or a dipole essentially if you just take a charged object and bring it near a neutral one, like we've been talking about. You can also do it with like an atom. So you just an external charged object is brought near a neutral object. And then the electrons, in this case in the atom, they will move closer to the external object if your external object is positive. And then the positive nucleus will be repelled. So this sort of creates a lopsided dipole. We can see that here. Here we have a neutral atom, nothing special going on, everything's symmetrical. You can see that everything's symmetrical on whichever axis you look at. But if we bring in an external charge, here's our external charge, that sea of electrons, they're oppositely charged. They're going to want, let me switch to blue, they're going to want to move toward that positive charge. It's different. They want to be there. But the nucleus, it also has positive charge. Like charges hate being near each other. So they're going to try and get away. Now remember, the electrons, they move easily, so they can get closer, and that force is stronger. We'll talk about that in the next lecture, why. But for now, just know that distance does matter. The closer these charge objects are, the stronger the force. So since the sea of electrons is actually just a little bit closer to the external charge, this force is going to be stronger than the repulsive force from the nucleus, from the protons. So when we sum the forces, this larger attractive force is going to win out at the end of the day. So we're going to get a net force toward the external charge. And we can actually have an externally charged particle that's either positive or negative. Either way, we get a net force in the same direction, but the dipole could be oriented in a completely different way. So you'll notice here we have a negative on the left, but then if we switch the external charge, we have a negative on the right. Hmm. So an insulator actually has no sea of electrons to shift, because remember, they're all tightly bound. So if an external charge is brought close instead of a big shift, what you get is individual atoms in the insulator become polarized. So this is what happens in an insulator. You don't get all the electrons moving to one side, but each individual atom sort of turns a little bit and tries to align to that external charge. So the polarization force acts on each atom individually and produces a net polarization. Okay. So they all sort of contribute to one overall net force, and it's going to be toward the external charge. All right, let's see. Let me check. Yes. Last little topic. I don't know why the book doesn't go into this in more detail, but something to think about is you can charge by induction. Um, And basically, this is if a situation where you can charge something by not actually touching it to redistribute charge, just doing some clever trickery to charge something. So essentially, if a distant object separates charges and the negative or positive charge, okay, so they're separated and then the negative or positive charges are isolated. Now let's think about this example. So first we have this electroscope plus human system. As you can see, it might be hard to see, but we have this electroscope, human system. They are touching each other. Okay, so this is all one big thing. Now, if we bring this charged rod, notice that they are positive. If we bring this charged rod over, we're going to move electrons through this conductor. They want to go up to meet this charged rod. The electrons in the person, they want to go over and meet this charged rod. Okay. So the number of electrons on the electroscope actually increases because we have the electrons from the electroscope from the scope plus the electrons from the human. Okay, so hopefully everybody sees how that works. Since we are getting some electrons coming from the human, it wants to go up and meet this charged rod that's external. Okay, so once that happens, um, we're going to have more electrons than normal on the scope, as you can see. Now, the trick is once we get those more electrons than normal on the scope, what's going to happen is the human is going to let go. Okay, so that means the human has lost some electrons, right? Is the human's going to have a little less than normal because they went to the scope. So it's going to give the human a net positive charge. And this electroscope, since it borrowed some of these charges from the human when they were one thing, remember, this is one system. When they were one thing, the electroscope got some extra charges. They're still there, but the human let go. So all those extra charges, those extra electrons, are going to make a net negative charge on this electroscope. All right, well, notice how they're clumped up. So the next thing that's going to happen, let's see if I have a bullet point. When the human breaks the connection, the electroscope now has a net charge. Yes, okay. So we talked about the breaking of the connection, the net negative charge. Okay, and now, as electrons do in a conductor, because this is a metal electroscope, the electrons will redistribute themselves. Remember, they hate being around each other, so they're going to redistribute everywhere, right? So that means they want to move down and away from each other. Now, if these two leaves on the electroscope are both negatively charged, they're going to want to separate. So you'll actually see these leaves start to move apart if you do this on a real electroscope. And that's why we have two force vectors, because these charges are actually providing a force to push these things away. All right. So I know this was dense, but we actually set the scene here to talk about Coulomb's law in the next topic. Um, so as always, if you have any questions about any of this, please let me know.